What if I told you that the planet humanity is spending billions of dollars trying to reach, isn't actually the best place to build our future? Think about it for a moment. Every time we talk about becoming a spacefaring civilization, one name dominates the conversation: Mars. It's in the movies, the headlines, the plans of billionaires, and the dreams of millions. We've become so convinced that Mars is humanity's next home that almost nobody stops to ask a simple question: what if we're wrong? What if the greatest city humanity ever builds in space isn't on Mars at all? What if, hidden in the darkness between Mars and Jupiter, there is a small frozen world with more water, more resources, and a better long-term future than the red planet itself? It sounds absurd at first. But by the end of this video, you may find yourself wondering whether Mars was never the destination, just the stepping stone that distracted us from something far bigger. Before we talk about Ceres, asteroid mining, giant space habitats, or the future of civilization beyond Earth, we need to confront a problem that sits at the center of every discussion about colonizing Mars. It's a problem so fundamental that it could determine whether a Martian settlement becomes a thriving civilization or remains a permanent scientific outpost. Yet despite its importance, it rarely gets the attention it deserves. Ask most people what the biggest challenge of living on Mars would be, and they'll mention the freezing temperatures, the thin atmosphere, the radiation, the dust storms, or the enormous distance from Earth. All of those are real challenges, and none of them should be underestimated. But there's another factor, one that affects every second of every day, every movement, every heartbeat, every biological process occurring inside the human body. Gravity. More specifically, the fact that Mars only has about 38% of Earth's gravity. That number sounds reassuring at first. 38% feels substantial. It isn't the near weightlessness of orbit, and it isn't the weak gravity of the Moon. It's somewhere in between, which leads many people to assume that it must be good enough. The uncomfortable truth is that nobody actually knows if it is. Gravity is so deeply woven into our existence that we rarely think about it. Right now, as you sit or stand watching this video, gravity is pulling on every cell in your body. Your skeleton evolved under it. Your muscles evolved under it. Your heart evolved under it. Your circulatory system, your balance, your posture, your movement, even the way fluids distribute themselves throughout your body have all been shaped by a constant force of one Earth gravity. We don't notice it because we've never known anything else. Gravity is the invisible architect of human biology. Remove it, and the consequences appear almost immediately. Decades of spaceflight have shown us what happens when humans spend extended periods in microgravity. Astronauts lose bone density. Their muscles weaken. Their cardiovascular systems adapt in unexpected ways. Their eyesight can change. Their immune systems can behave differently. Despite rigorous exercise programs, the human body struggles when gravity disappears. The International Space Station has taught us a tremendous amount about how humans function in space, but it has also revealed a major limitation in our understanding. We know what happens at 1 gravity. We know a fair amount about what happens at nearly 0 gravity. What we don't know is what happens in between. This gap in our knowledge may be one of the most important unanswered questions in the entire future of space exploration. Mars operates in a gravity environment that no human being has ever experienced for an extended period. Nobody has lived for years at 38 centimos. Nobody has raised children there. Nobody has grown old there. Nobody knows whether the human body can remain healthy for decades under those conditions. It's possible that 38% gravity is sufficient to preserve most aspects of human health. It's also possible that it isn't. The problem is that we won't know until people actually live there, and by the time we discover the answer, generations of settlers could already be committed to a world they cannot easily leave. Imagine the first child born on Mars. It's a milestone many people expect to happen within this century. That child would be the first human being in history to spend every moment of life under a different gravitational environment than the one that shaped humanity for millions of years. Their bones would develop under lower mechanical stress. Their muscles would grow in a world where every object feels dramatically lighter. Their cardiovascular system would adapt to conditions no human physiology has ever encountered before. What would adulthood look like for that child? Could they run, jump, and function normally by Martian standards? Probably. But what would happen if they traveled to Earth? Could their body withstand the full force of Earth's gravity? Or would our home planet feel crushingly heavy, almost unbearable? The answer isn't known. That's not science fiction. That's a genuine scientific uncertainty. Many Mars advocates tend to treat gravity as a solved problem simply because Mars has more gravity than the Moon. But biology doesn't care about assumptions. Biology responds to physical reality. There may be thresholds below which human development becomes compromised. There may be minimum gravitational requirements for healthy bone growth, proper cardiovascular function, reproductive health, or childhood development. We simply don't know where those thresholds lie. Some researchers believe that Mars gravity might be enough. Others are far less certain. The issue becomes even more serious when considering multiple generations. A temporary mission lasting a few years is one thing. A civilization expected to endure for centuries is something entirely different. Colonization is not just about survival. It's about creating a sustainable environment where future generations can live healthy lives. Consider the history of exploration on Earth. When humans crossed oceans and established settlements on distant continents, they entered environments with different climates, different diseases, and different ecosystems. But one thing remained unchanged: gravity. Every human civilization in history developed under exactly the same gravitational conditions. The first Martian civilization would be the first experiment of its kind. We would not simply be moving humanity to another location. We would be testing whether our species can permanently exist under a fundamentally different physical environment. That's a much larger leap than many people realize. Then there is the issue of long-term health. Bone density loss is one of the clearest concerns. On Earth, our skeletons constantly remodel themselves in response to mechanical stress. Gravity creates that stress. When astronauts enter microgravity, their bones begin losing density because the body no longer sees a reason to maintain such robust skeletal structures. Mars gravity may reduce that effect, but by how much? Is 38% enough to prevent significant degradation over decades? Again, nobody knows. The same uncertainty applies to muscles. Humans evolved in an environment where movement requires effort. Lower gravity changes that equation. Tasks that would normally require strength become easier. Over time, reduced physical demands may alter muscle development in ways that are difficult to predict. The cardiovascular system presents another challenge. On Earth, gravity forces the heart to work continuously to circulate blood throughout the body. In space, fluid shifts occur because gravity no longer pulls blood downward in the same way. Astronauts often experience facial puffiness and changes in circulation. Mars gravity would create a different balance, but nobody knows whether it would be sufficient to maintain normal cardiovascular function across an entire lifetime. Small changes accumulated over decades can have enormous consequences. Perhaps the most profound question involves reproduction and development. Humanity has never conceived, carried, and raised multiple generations in reduced gravity. Animal studies provide some clues, but they do not provide definitive answers. Human development is extraordinarily complex. Pregnancy, fetal growth, childhood development, adolescence, and aging all involve biological processes that evolved under one gravity. Changing that environment introduces uncertainties that science has barely begun to explore. If humanity intends to become a multiplanetary species, these questions cannot be ignored. This is where the debate about Mars becomes more complicated than most public discussions suggest. The popular narrative often frames Mars as the inevitable next home for humanity. The challenge is portrayed primarily as an engineering problem. Build rockets. Develop habitats. Produce food. Generate power. Protect against radiation. While those are certainly difficult tasks, engineering problems can often be solved with enough resources and innovation. Gravity is different. Gravity isn't something you can easily fix on a planetary surface. You can't increase Mars' gravity. You can't install a planetary-scale machine to make the planet more Earth-like in that regard. Mars is what it is, and humanity would have to adapt to it rather than the other way around. This reality has led some scientists and space visionaries to rethink the entire approach to colonization. Instead of asking which planet is closest to Earth-like conditions, they ask a different question. What if planets aren't the ideal places for advanced civilizations in the first place? What if the future of humanity in space isn't about finding the right world, but building one? It's a radical shift in perspective. For centuries, humans have searched for habitable land. We assume civilization requires a planetary surface because every civilization in history has existed on one. But space offers possibilities that Earth never did. Instead of accepting whatever gravity a planet provides, artificial habitats could generate their own through rotation. Instead of being limited by the resources available on a single world, they could draw materials from entire regions of the solar system. The gravity problem is one of the reasons this alternative vision is gaining attention. If Mars' gravity turns out to be insufficient for long-term human health, then every settlement built there faces a fundamental limitation. Artificial habitats, on the other hand, could be designed to provide Earth-normal gravity from the beginning. Children could grow up under conditions nearly identical to those on Earth. Future generations would not be biological experiments. They would live in environments intentionally engineered around human needs. None of this means Mars is a bad destination. Mars remains one of the most compelling targets for exploration in the solar system. Its relative proximity, geological history, and scientific value make it enormously important. The first human footsteps on Mars will likely be among the greatest achievements in human history. But exploration and civilization are not necessarily the same thing. The first place humans visit is not always the place where they ultimately choose to build their largest cities. History provides countless examples. Early settlements often emerged in locations that were later surpassed by places with better resources, better trade routes, or better long-term prospects. What makes the gravity question so significant is that it forces us to think beyond the excitement of first arrivals. It forces us to ask what comes after the flags, after the headlines, after the historic landings. What happens when there are not hundreds of people on Mars, but hundreds of thousands? What happens when families, schools, businesses, and entire communities begin to emerge? What happens when humanity stops treating Mars as a destination and starts treating it as a home? At that point, questions about long-term health become impossible to ignore. And that is why some researchers have begun looking elsewhere for answers. Not because Mars lacks potential, but because the future of civilization may require solutions that go beyond planetary surfaces altogether. The gravity problem is not merely a technical detail buried in scientific papers. It may be one of the defining challenges of humanity's expansion into space. Until we understand it, every vision of a Martian civilization contains a major uncertainty at its core. The dream of Mars remains powerful, inspiring, and worth pursuing. But before we assume it is humanity's ultimate destination, we must confront a simple reality. The most important question about living on Mars has not yet been answered. And until it is, the search for a better alternative remains one of the most important conversations in the future of space exploration. Now that we've confronted the gravity problem, a question that could shape the future of every Martian colony, it's time to turn our attention to a place that almost never appears in discussions about humanity's future in space. Ask the average person to name destinations for human settlement beyond Earth, and you'll hear the usual list. The Moon. Mars. Maybe Titan. Perhaps Europa if they're particularly interested in science fiction. But very few people mention Ceres. In fact, many people have never heard of it at all. And yet, this small dwarf planet may possess some of the most valuable characteristics of any object in the inner solar system. The strange part is that Ceres isn't hidden. It isn't lurking in some distant corner beyond Neptune. It sits in one of the most studied regions of space, right in the middle of the asteroid belt between Mars and Jupiter. Astronomers have known about it since 1801. It was discovered by Giuseppe Piazzi on the first day of the 19th century, making it one of the earliest objects ever identified beyond the major planets. For a brief period, it was even classified as a planet. Then it became an asteroid. Then, in 2006, it joined Pluto in the newly created category of dwarf planets. Throughout all those changes, one thing remained constant: most people paid very little attention to it.